Check, check, test. Okay, yeah, not too many people here yet, but I'm gonna go ahead and start. Yeah, just two of us at the moment. Yeah, people usually roll in a couple minutes after, but I'll probably repeat some of these announcements at the end too, just to make sure everybody knows them. Um, Morning. Okay, so just kind of reminder where we're at. I do have there's our next assignment is due on Friday this week. I did have a question about submitting these things. I do have deadlines on Fridays for the assignments. It might say like 5 p.m. or something, but and generally, it probably is okay if you keep working on Saturday. I have reasons I have to do them over the weekend. I can't do stuff on Mondays. I kind of like to have the stuff done so I can return it back and discuss it on the Tuesday after. So anyway, somebody did ask about that, and sorry about that. I can't really move that. So it'd be a good idea to make sure you get stuff submitted by Friday. If you do need some extra time, do kind of let me know. Like I said, generally Saturday is fine, although I usually have to begin evaluating stuff on Saturday. But if you let me know, I can put yours to the last, or maybe do it like Sunday or something. But yeah, do try to get the stuff in by Friday. I mean, another thing, if you are like you've got a job and you're doing stuff during the week and you do most of your work on the weekends. I do suggest that you maybe consider the weekend before as the deadline, as your own personal deadline for getting these, or at least mostly getting these done, if at all possible. And actually, for all students, it'd be a good idea to, assignments like these to not wait till the Friday to get started on it, or the Thursday or something like that. Most people are fine, but people will run into technical problems, or you'll come up to a question on something where if you could just send me an email or talk to me in office hours, it would be an easy kind of thing, but you end up being stuck on it if it was after too close to the deadline or something. So I mean, it's just a word of advice. Of course, everybody's different, has their own schedules and things, but yeah, for reasons they do have to have the stuff turned in by Friday so I can look at it over the weekend and things. So just keep that in mind. There's actually two things for this Friday, so don't forget about also the. I did ask you to accept the assignment for the final project and pick a data set. So I had a couple of people ask questions about those, and I haven't checked to see how far people have gotten on that, but don't forget that as well. So I am looking for you to make a commit on that as well, where you've modified the README and gave me the information at least there about the data set you're asking for. And I'm going to try to look at those as well on the weekend, at least to make certain that nobody's asking to do a data set that might be problematic or something. I don't know if I've explicitly stated this. But some simple data sets you will find on some of those links that I gave. So things like the wine data set or the MNIST data set, things that we tend to use as examples in class, or that would be used as examples are easily found on the web. I'll probably push you away from using those. So there's a couple kind of standard data sets that like our textbook uses or other textbook uses a lot. I would ask people not to use. So, but like I said, but make sure you do that by Friday as well, and I'll try and check those just to make sure nobody's doing something that I want them to not do to push them away and pick something else. So yeah, let me know if anybody has any questions. Like I said, I've been getting some emails about that. So question about your data set. I mean, you can just specify in your README what you want to do, and I will look at it at some point and give you some feedback on that if it's not acceptable or not. But if you have questions, go ahead and email me. A couple of people have their own kinds of data sets from work or things that they wanted to work on, which is great. And have been asking to use those and things. So. All right. So let me get to change over my desktop here. So with that, I'll get into my plan for today was I'm going to talk kind of just about linear and logistic regression. So if you're following up with the materials I'm asking you to look at for the class, we should be looking at the chapter 3. So we're back this week, the one after the end-to-end example, where we're beginning to talk more specifically about doing classification problems. So chapter 3 is, on this week is all about, just verify I'm getting right, yeah, the right chapter number. So chapter 3 from our textbook is all about classification versus regression problems. I'm going to talk a little bit about that today. In fact, I think I'll just spend the whole day mostly on this particular notebook here, because this is also relevant to the assignment that you should be working on for this week, or second assignment. I'm doing linear and logistic regression with the stats model and the scikit-learn library. So I've got the repository open up here, our CSci 574 ML repository, and I'm running, I've done the usual things. I'm running the Jupyter Lab notebook here. So I'm talking about this one here. I had mentioned this one, the notebook 3-4. So this isn't really from our textbook. The 1, 2, and 3 are just directly from our chapter 2 textbook, the end-to-end thing. I didn't talk a whole lot about those in class, but there are videos on me kind of going through that stuff. So I wanted to mention, and kind of sorry about this, I didn't get a chance to check all these. So there, any place that's using trying to set the backend from matplotlib rendering to inline is probably not working. Something has changed. So you do need to comment that out. In fact, I actually did fix that, and there was something not working in this notebook as well when I ran it. A parameter for logistic regression. Not the linear regression, but I think it was down here to where we did logistic regression. I'll come to it, but yeah, down here there used to be a parameter you could specify if you wanted to use a classification problem that wasn't binary, that had more than 2 classes. You could set a parameter there, but apparently that's gone away since the last time I ran this notebook. So anyway, this notebook wasn't running. Not to mention also, I don't know if there were some links on here, but 1 or 2 of these were broken. Although I know I checked those not too long ago, but yeah, the space, these things are changing quite quickly, so websites come and go with things. But I did commit this and push that on there. So I wanted to mention before I get into this that I might occasionally, I don't know if I'll need to much for this class, but if ever I need to add new material or update stuff, I will make a commit and push it in there and tell you that you can do a poll. So if you're using VS Code for your source control, you can do a synchronize or a poll. So like if you do push the bottom button down there, any changes that I make will get pulled down. Although I should warn you that if you pull down the change that I just did here, if you had also been using this notebook 3.4, because that was the one that I just made some fixes to here that I was discussing. So if you made some changes to this notebook and saved it, and then you did a poll, you might get a conflict. There's a merge conflict because your changes in this notebook are different. So your notebook now is different from mine. So in general, that is just using Git when you're working with other people on a project. you have to worry about that stuff. But here, I'm really only using this repository as a way for you to download stuff. So if you do get a merge conflict, I just recommend just deleting the IPython notebook and doing the pull again. It will just pull down the version that I have up there. Unless if there is something, if you were working on these and there was some stuff you want to save, just rename it to something else, and then do the git pull. So we just rename it like put your name on the end of it or version 1 or something like that. So you can always do like a right click on there, on the file browser, or on your local file system. It can open up in the file browser and like right click and do a rename, or an F2 rename and put your name on there, B1 or something. It just if you do get a message about merge conflict, if you want to pull down changes, if I put new stuff up there and you get conflicts, just rename it or move it somewhere else and do the pull. It will. So I'll show it here. So I'll change the name of that file. I'm gonna remove it. I'm gonna stop it out of my Jupyter Lab server here on my web browser, and I'll do the sync again. It'll just pull down the version. So now that the file is missing, it will pull down the version on the remote repository. If we do a sync, it should. Yeah, I thought that would automatically just pull it down to a certain one. So yeah, just give me a second here because I do want to pull that back down. So yeah, usually when you delete something off there, you need to just do a pull. Oh, I guess maybe because it's, yeah, if you do have local things modified, stage all these. Certain. Yeah, I'll come back. So yeah, what I was saying there might not be true. So if you do have local modifications, you might have to like stage them or stash them or something like that. So restore that file locally. Anyway, yeah. So I'll come back to that. But as I was saying, then the general point is for these files, if I tell you that there's some new stuff, you might need to do a git pull or something. And there were some, when I come up to them again here talking about these, there was at least one cell that wasn't working, so something had changed since the version that I made this last time I checked this notebook here. I'll mention that again when I come up to that point there. So, but yeah, you might have had that problem if you. Okay, so like I was saying, I think the thing I was just going to concentrate on today was talking about doing linear and logistic regressions using scikit-learn stats models. So this is really pretty much the paralleling what you're supposed to be doing for the assignment as well. So I can just mention a couple of things about stuff if we look through this notebook here. So, we are probably on Thursday, I want to talk a little bit more about the details of doing classification. So logistic regression is really where you're doing building a classifier instead of a regressor. And then next week, we're going to get into the details of how these kinds of models actually work, right? So some of this stuff, if you've never, studied linear regression or statistics class or something like that, might be unfamiliar to you, but this will make some of the details about some of the things you're supposed to do on this assignment will make more sense when we talk about what it means to fit a set of data into a model, what the fitness functions are, and gradient descent, stuff like that. So that's coming up kind of next week here. So yeah, some of these links were broken. I put some new ones in there, although, if you don't want to pull down the notebook, usually if you just, like Google, usually stuff from like Medium or KD Nuggets or data science websites has pretty basic but good tutorials. So the stuff that's usually at the top of the Google, if you're looking for logistic regression using scikit-learn or logistic regression using SAS model. If you're looking for more examples of doing this kind of stuff. That was kind of where this notebook came from. I was kind of reading through examples of other tutorials of doing these things. Let's look at scikit-learn. I think we've mentioned most of the stuff pretty quickly in this class. We will be using either NumPy arrays or pandas data frames. So scikit-learn, when it was first created, it was kind of the pandas data frames weren't around. So initially, scikit-learn only used NumPy arrays, but it does support pandas data frames now. So you can actually pass in a pandas data frame or a NumPy array if you want to as the set of features or target vector to train with, or a NumPy array. So, in fact, that was it's been around for a while now. Scikit-learn is much higher now in version 0.20. So most everything that we do in this class, traditionally, we're going to have a feature matrix and like a target vector. Traditionally, we'll just generically call the feature matrix X, and for mathematics, we usually use capital letters for two-dimensional or higher for matrices or general tensors, and we use lowercase for vectors. So you'll often see it as a big X and a lowercase y if you see tutorials doing stuff like this. But so for linear regression and classification problems, these are examples of supervised learning, right? So if you read the chapter 1, it talked about kind of the big picture kinds of things in machine learning. I haven't talked a whole lot about those in class. So for these kinds of supervised learning, when we're fitting a model or training a model to a set of data, you have to have to do the training of the fitting for each sample. So each row is going to be a sample in our data set. And if we're doing multi-feature regression or multi-feature classification, we can add multiple features. So each column represents a feature. We'll see an example detail of this here in just a second. But for each one of these, if we want to fit a model like a linear regression, for each one of the input samples, we have to have a target or what the correct answer is. So that we can, the process of fitting a model is finding a set of parameters that will transform. So we have some features we've never seen before. We want to predict what the target would be. And we want to have a good prediction, so close to what the true target would be for some sample or some number of samples that we've never seen before. Okay. So in general, we're always going to be working with a two-dimensional matrix, which will have what conventionally we use like n for the number of samples, so the number of rows, and m for the number of features. Hopefully, I can get that twisted around backwards. And so when we're doing supervised learning, the target, so that y has to have the same number as the number of samples. So if n is the number of samples, or n samples is the number of rows that we have to have n samples targets for doing supervised learning. So we'll get concrete on here. So we have another data set here that we're going to be using in this notebook if you haven't looked at it. But the scikit-learn API, so part of the goal of this class is to actually learn the details of how different machine learning models work, right? So we will, starting next week, get into a bit of the details of how linear regression, logistic regression work, and then also look at support vector machine and a couple of other the more important ones, the inner workings of what it means to fit a model to a set of data. But you can't, without really knowing or understanding kind of how that works, you can still do machine learning by applying the scikit-learn API. So the general steps, and you're probably already familiar with this from doing the readings anyway at this point in class if you've done nothing else, is we do have to arrange our data into two matrices like that, usually a two-dimensional feature matrix and a target vector. Then we have to, for doing stuff with scikit-learn, scikit-learn supports all kinds of different machine learning models. So we have to choose our class and import that appropriate, these are usually called estimators. So if we're doing supervised learning, an estimator means that when we fit the model and we ask it to make a prediction, it can estimate what the output should be from the model that we created and fit for set of data. So we'll look at linear regression and logistic regression here, but there's others. Scikit-learn supports all the major ones that any model that you're likely to want to use probably has been implemented in scikit-learn for machine learning. When you instantiate this model, often in this class we will want to select what are known as hyperparameters. So we don't have any good examples, real good examples of that on this assignment, but I'll discuss that in a second. And then we're going to do what's called training the model. So in scikit-learn, that's just basically going to call the fit function where we pass it in the feature matrix and the target vectors if we're doing supervised learning in order to train or fit the model. And then once you have a fitted model, I mean, the thing you actually want to do with it is make predictions on data, on new data that's never been seen before. So, one of the things you have to do on this assignment you're working on right now is you have to get the parameters from the fitted model and do some stuff with them, and you have to call the predict method, I believe, to make some predictions, to get some idea of how well it does on unseen data. Okay, so to get specific, in the chapter from last week, it was using some California housing data. This is again housing data, although it's slightly different than the one used in chapter 2. You should have just read through here. But that data set is in there. If you read that into a data frame, you'll see that it has 6 different columns. Again, pull up the raw data frame real quickly for this one. So if you look at that, it's got got one row in the file which actually has column names, column separated. So we've got 6, 1, 2, 3, 4, 5, 6 or 7, I guess. We have 7 different columns in the original one. Most of these are similar to the ones in chapter 2 here, like the average income in the area and things like that. And for a regression problem, remember the label or the target is going to be a real value number. So we've got a value in dollars, I guess. So a lot of these are 100,000 or a million or more. These are some houses in California, more recent data. So many of them are above 500,000 or a million for price. Unlike the data in the chapter 2, I think these are actual individual houses because we've got an actual address for the house. Although we do have information about what the income is on average for the area where the house is and the age of houses in the area and stuff like that. So most of these other things are similar to what we're doing in chapter 2. Data about other houses in the area. This house, the size, the number of people in that area. So, and there's 5,000 here. So the feature matrix. To jump ahead here a little bit, the price is going to be our target for the regression that we want to do. So we need to create a new matrix where we remove that out, and that becomes our y, or the vector here. We'll go ahead and use all these numeric ones. So all these are numeric, and there's no missing data. There's like 5,000 samples. So we've got 5,000 rows in this data set. So 5,000 example houses, and we want to train with. We are going to also drop the address. So this address, we can maybe do something with it, but that's just textual information. So we'll use that in this example here. So on this assignment, you're asked to do some similar stuff here. You know, like if you want to get information about the types of the numeric columns, we could use info, or we could use describe. We use describe here. We could use describe to get on a pandas data frame, like we did here, to get summaries. Info and describe give summaries of columns that were interpreted as numeric columns. Right? So this one can be particularly useful to get a first glance of what the range is of the data, so what the average of the data is, and where it goes from the min to the max on our numeric features. So okay. So on your assignment 2, I think you're asked to do some other similar stuff like this. So one basic thing you might want to do when you're doing your initial data exploration is get an idea of how correlated your different columns, your different features are to what you're trying to predict, right? So like one basic way you could do that is just do a scatter plot. This function from Seaborn does a scatter plot of everything versus every other feature, right? Pair plot here. So, but yeah, the most useful thing would be to look at like price, either the price row or the price column. So in general, I mean, all of these kind of look like they are positively correlated. Right? So, I mean, there's a lot of noise, but they're going kind of from left to right. They're going from lower to upper, mostly. Right? So it looks like, just looking at price, I mean, although some of these are more blah, blah, and you kind of see that you don't have that as much. Like if you look at, like here we're doing the correlation between house age and population. Right? So whenever you see just a circular blob like that, there's probably not a whole lot of high correlation between those two. But we are getting something between price and most of these others. Maybe number of bedrooms is a little bit tougher to see, but number of bedrooms must be a categorical feature there. 1 bedroom, 2, 3, 4, 5, instead of a real value number. We get things like that. Although, yeah, you might have been asked to do directly apply a correlation. Correlation. So this is another thing that I fixed, but I guess that when I deleted it, it didn't pull it back down. Hopefully my fix got pushed up there. The correlation will only work on numeric values. The data frame as we have it right now has one non-numeric feature, the address. So if we want to get this to work, we need to go ahead and try and do a correlation, but only have a data frame with a numeric feature. Something like that. Yeah. So this can be more useful when you're doing initial data exploration, having an actual numeric value, measuring probably the Pearson correlation or something like that here. But yeah, again, when you look at the price, so if you've never seen it, we're correlating kind of like the pairwise plots. We're correlating, doing a Pearson correlation between every feature and every other feature. So each feature has one means that it's perfectly correlated, which we would expect if you correlate the feature with itself. So, and we don't have any negative correlations in this data set here, although for the data set you're working on for assignment 2, so correlations can go from 1 to 0, but also down to -1. It's kind of a hint for you guys that are in here or watching this video. The magnitude of the correlation is what's important of whether a particular feature will be useful, might be more useful or less useful for predicting a target value. Right? So things that are close to 0, there's not a lot of correlation, so it might not be very useful as a predictor. So the lowest correlation we have is the 0.17 on the number of bedrooms. But things that are close to 1, or even things that are negative, so highly negative correlated can also be a useful predictor. So it's how far away from 0 you are. It's really the important thing on whether a feature ultimately might end up being a good predictor for a target. And probably not unsurprising for this one, I think we had a similar thing on the data set in chapter 2. If the area income has the kind of the highest correlation among the features that we have here, which shouldn't be surprising because the higher the income is in the area, probably the higher the price houses are for the people living in that area. But notice everything is positively correlated, right? So again, you can kind of guess that from the pairwise plots. They were noisy, but they did seem to have a correlation positive. So kind of lower when price is low, going to higher. Okay. So yeah, I did want to get to talk about stats model and logistic regression. So I should go ahead and speed up a little bit. So kind of finishing that up. To finish up the steps for using the scikit-learn API, steps 1, 2, 3, 4, 5 that were mentioned there. So we're going to do a linear regression. The normal thing you'll be doing for notebooks for assignments in this class is we'll just directly import a particular scikit-learn model from some sub-library of scikit-learn. So you'll learn what we mean by a linear model versus a nonlinear model. We'll go into a little bit of details of that when we talk about linear regression, logistic regression. So we're just going to use linear models are simpler than nonlinear models. So we'll just import a linear regression, which is a type of linear model. Here, we're not using any metaparameters. Here again is where either looking at the documentation online or using the contextual help can be useful. So, for example, these are actually the metaparameters that we could have modified. There's not a lot for a basic linear regression. We can change like the tolerance or this copy X I might come back to. So this is determining whether, sorry, not copy, the fit intercept is determining whether we're going to fit an intercept parameter or not. which is similar to the idea of whether we need to provide a dummy set of a dummy feature for the intercept parameter or not. That we'll get into here. But yeah, so we're not doing any meta parameters here, but this is where you would specify those. We'll do some of these for logistic regression. So once you have a model, I mean, all these, no matter what you're doing, linear regression, support vector machines, kind of a tree or something, after that, the way you fit it and use it is usually similar. So fit almost always looks like this when you're doing, it always looks like this when you're doing a supervised learning. So you just pass in the feature matrix, which should be two-dimensional, and the target vector, which should have the same number of items as the number of rows or the number of features that you have in that, or else it won't work. And kind of as an aside, as we'll see for the stats model passes in y first, followed by x, which it can be confusing if you don't understand why, but that was the convention that the stats model library uses when statisticians think of fitting a model. So they kind of reverse the order of those two parameters when you pass it into this to do a stats model fit. So yeah, I don't think I'll rerun this. So I think I do ask you to do some similar stuff like this. So once you have a model fit, does everybody? We're basically we're using the object-oriented way that Python works here. So a model that we instantiated and fit here is just an object or a class. And after the fit, we actually, these are the things that get set when you train a model to a set of data so it can make good predictions. So the coefficients and the intercept parameter are the things that we will have for a lot of the types of models that we work with in this class here. You'll understand. So you'll notice, though, that kind of as a hint of what these are, is there's going to be one coefficient, one of these parameters, for every one of the features that we train with, right? So for a linear regression, really what's happening, if I want to make a prediction on a new set of data that I've never seen before, I'll have to pass in what these values are for the new house that I want to make a prediction what the price is. And we're just going to end up multiplying these coefficients times, whatever the average income is for the new house, and that coefficient gets multiplied by the house age, and so on, and then you sum those up, and that ends up really being your prediction for a linear regression. It's really just the sum of these times the new value you're trying to predict. That's what the predict method is doing. To fit, so one of the things you're supposed to do is display a line to visualize the fit of your linear model to the set of data. So if you only have one feature, you'll have your feature and your intercepts, and you can use those to actually directly create your lines. So show the model that was fit to the scatter plot. Maybe I should bring up the assignment at some point, but that was one of the things you were supposed to do for your assignment 2 here. Okay, but yeah, so you'll have to. I started saying that these really the model is just it's just an object. So we can call member methods on the object like predict, but the coefficient and the intercept end up being just member variables. Right? So the coefficient is like an array, a NumPy array probably. So what is the type of? So probably have a different model created. So I need to rerun everything above that. Get it back down to here. So yeah, it's just a NumPy array, right? So these things in the coefficients is just a NumPy array, and the intercept is just a regular floating point value. These are just member variables. Model here, active fit. Those will be parameters. The underscore, by the way, at the end means that it's really kind of an internal member parameter, member variable. Okay, then so once you have a set of model, a model that's fit to a set of data, you can use predict. So here, I mean, you can try your predictions on the original data. So the stuff, and another thing to know about predict is you can pass in more than one sample to make a prediction of. So if I pass in X, it will make predictions for all of the, the 5,000 samples that we have here. So here we're showing the kind of how close, this gives us an idea of how close the predictions were to the true value that we have. So if we were perfectly correct for every prediction, it would just be a straight line. Of course, we can't get perfect prediction with this data. There's some noise in it. So yeah, I wanted to get to looking at stats model. So let's just kind of mention these things. I think you do have to do some train test splits on the assignment too. So usually, instead of what we just did before, if we want to evaluate the performance of a model, and we only have so much data, we will normally train it with only a portion of the data and hold back some of that so we can evaluate it on the data it hasn't seen before. So making predictions on data that you fit the model with is not going to give you the best idea of how good your model is, because you can do what's known as overfitting. So you can make a model that will perfectly predict the data you fit it with, but it won't do well on unseen data if it's overfit. There's often ways to overfit models, so it's a general problem in machine learning. So the normal way to find that in machine learning is we only train with part of the data, and we're going to evaluate the data we've never seen before. That will give us a better idea of how the model generalizes, how it makes predictions on unseen data. So like if we split off 70% of the data for training, it only fit with the training data, then we can get an idea of predicting just with the test data that we didn't actually fit for training. So one measure, I think I do ask you to give like the mean squared errors or the root mean squared errors for these models. So for a logistic regression, usually the mean squared error or the root mean squared error will be what we use as a measure of how well the model is performing. So basically, the bigger this number, the more error it has. And the smaller this number, the better it's predicted. But so we can ask for the mean squared error, given a set of predictions, right? So if we predict on the data that we trained with, we can find the mean squared error, the root mean squared error. So we're getting these values, pretty big. Although I don't know if I've mentioned this before. So usually, if we want to get an idea of in real units, we want to take the square root of that mean squared error, so that will convert it back instead of the square of the errors, the error. So the way this is normally interpreted is that on the data we trained with, we're about $100,000 off on our predictions. But again, this is not necessarily a good, if the model is overfitting, we could have a very small mean squared error, root mean squared error on the data we trained with, but you'd end up with a really bad prediction error on unseen data. But that's not the case here, so we're getting a similar, so if we do the same thing, but on unseen data, we get about the same root mean squared error, about the same for the other thing as well, which is probably evidence that we're not overfitting. So we did okay fitting this linear regression model. Yeah, we'll probably get more into that in this class. When you are building multiple models, we're only building one model here, but like if I want to build a model with a linear regression and maybe with a support vector machine and a tree, if you train the model, especially if you're doing some iterations on models like that, where we're trying different meta parameters. So the problem is that you can end up overfitting. You keep evaluating just on your test data, but you do that for multiple times for different models or for different parameters for the same type of model. You can get another subtle introduction of overfitting. So the normal way that is solved is we split things up into three: a train, a validation, and then a final test. So normally, if you're doing a lot of modeling, you will validate it with the validation training set. But then at the end, once you've picked a model, you probably would do a final test with a held back test set that was never used before, just to make a final check that I didn't get some subtle overfitting when I was iterating different meta parameters.
Instead of evaluating training and test, we will evaluate validation and testing.
So yeah, in fact, the next third assignment we'll be doing something like that. But that is often the case. We will split things up, and we will get more details of why this is. It's not quite making sense here, but that is a common workflow. So we would split things up into train, validation, and test data sets. When we're comparing and training multiple models, we would train them and use the validation data to get a feel for how it's doing. Once we're kind of getting near the end and are ready to pick a final model, we would use the final test set to ensure that we didn't get any subtle overfitting introduced when we were iterating over training multiple models. But yeah, I think for the assignment 2, you're only going to do split into train tests. We will do some, probably the next assignment we'll talk a little bit more about that issue. So I want to, we still got Thursday to talk about some stuff. So I'll just mention about logistic regression here using scikit-learn. So as you're reading the stuff from the chapter 3 for this week is all about classification, right? So we've mentioned this before, but classification is fundamentally the goal is the same. So we're doing supervised learning here. It's just that the targets are going to be discrete labeled values, right? And the simplest is going to be a binary classification where we're going to do yes or no. But we can also do like a multi-class classification. So in this case, we're using this M and IST training set. If you looked at this notebook here, where what we want to do is build a predictor to predict these to predict the digit from an 8-byte a set of pixel images here. So so the digit could be one of 10 categories, 0 through 9. So this, if we wanted to do the full MNIST, this would be an example of a multi-class classification. But if you look at how this works, you know, in terms of using scikit-learn, even though in logistic regression, the name might be a bit confusing, but we really are doing a classification here, even though it has regression in the name of the model here. That's a historical. We really are doing making a model classifier in this case here. But in terms of using the API, it's pretty much the same as we did for the linear regression. So we would import logistic regression instead of linear regression this time. This was the cell that wasn't working. So something has changed where you used to have to specify them doing a multi-class classification, but I guess it can handle that now just by looking at the data that we gave them fit. So, although you won't get convergence if you use a different solver. So here we're using a meta parameter, so we're asking to use a different optimization method than the default. So the default one doesn't converge. So it's better to use this solver here in this notebook. But yeah, so we create the model, we fit it. Here we've already split the data into train and test sets. So we train it with training data. Here, since we have an 8x8 set of pixels for our features, that means that we actually have 64 features here. So if you look at the coefficients, this array, there should be like 64 of these coefficient terms. Or something like that. Okay, yeah, and so I'll go ahead. So you can do the similar kinds of things at the end. For example, using predict to see how we did on our accuracy on trained data, but also on testing data. So let me quickly do stats model. We can do some more on this on Thursday as well. People have questions on it. So there are more libraries than just scikit-learn for doing machine learning or statistics. So stats models is more focused for kind of traditional statistics rather than what we would call machine learning. So, I mean, they're definitely very related, but slightly different. So if you want to use stats model, you can do logistic regression and linear regression. So the normal way that we import for doing stats model is import the stats model API as SM, and then use SM to do different things here. So stats model, because of the way that statisticians normally do things, they assume that the data has already been centered, so you don't really have to fit an intercept term. And again, I'll talk some more about this as well when we get to the details of linear regression. But that means that if you have a set of data, that you would either have to kind of center it the way it's expecting, or what you need to do for our assignment is we have to add what's known as a dummy constant. So if you look at, so we did the same thing we did before here, where we created X and Y, dropping the non-numeric and removing the price, because we want to use that for our target, for fitting our model to predictions on. So if you look at that before, we'll just have those five, I guess, the 5 features here that we had before in X. So when you add a constant like this, so it just adds in another row, another column of all ones. That's all that's being done. So if you look at, let's look at the head. I should have done it beforehand, but if you look at the head of this after we do this, basically now we've got 6 columns instead of 5, but that dummy constant column, all the values are 1. So that's needed since we didn't center the values here if we want to have the model fit not only the coefficients but also the intercept term as well. So for stats model, we explicitly have to add in that. I pointed out before, there's a meta parameter for scikit-learn. We can do a similar thing by having it fit the intercept or not with the meta parameter linear regression scikit-learn. So yeah, in stats model, so if you read the documentation for the linear regression for scikit-learn, if I can look at it real quickly here. Let me open up the contextual help. So another name for linear regression is an ordinary least squared model. Well, OLS. It's just called linear regression in scikit-learn, but in stats model they use the OLS as the name. So that's what we're doing here. So, and again, instead of just importing from the stats model library, I don't know, I mean, whenever I see people do stuff, they often do it like that. So they just import the stats model API, and then they just want to use the linear regression, which is called OLS, or ordinary squared from stats model. They do a create. So this is doing the same thing as, this is really fitting, sorry, no, yeah. This is actually creating an instance of the object. So notice also the API is a little bit different here in that we don't pass the parameters in when we do the actual fitting or training. We pass it in when the model is created. Again, in the reverse order and with the dummy intercept constant column add to X here. But there is similar, so you create the model and you fit it, although you pass it the parameter create it, so you fit it. But this will fit the model here for our stats model. When you do that, you'll have similar things, although you might have to read the documentation or look at the examples in this notebook. So you can get the access to the fitted parameters. Right, so instead of having the intercept and the coefficients, we've got something called params in our stats model OLS object here. But the same thing. If you compare these should be exactly the same values as the parameters that we got from fitting in scikit-learn, I believe, or at least very close. Okay. But yeah, as the final thing for today, I think I do ask you to also use a summary. So, and I might ask you to report the R squared value. I want to, maybe Thursday, I'll talk a little bit more about some details on this. This is really useful if you're doing kind of standard statistics, like if you're analyzing for a scientific paper. You might want this information here, right? So we're seeing all those same coefficients for the fitted model here, but we're getting information about the goodness of the fit for each of the models. So including the p-value and the 95% interval. So what this is basically saying to me is that so low p-values are good. So everything except for that one had pretty good fit, and this gives you a 95% confidence interval that the correct true value for this constant is probably somewhere between that and that, right? Where this will be right in the middle. But yeah, I can talk more about those, about the R squared, but you do also have to pull out the R squared, or I asked you to, from scikit-learn and also from the stats model, I think. So this is similar to the mean squared error. So it's kind of like a normalized mean squared error. So you can kind of think of this as, again, the goodness of the fit. Although, since it's normalized, what ends up being is that if you have a 1, you have a perfect fit, and if you have a 0, there's like it's a completely, there's no fit at all on the data. Right? And then so the higher, closer to 1, the better fit is on this R squared measure. Okay, yeah, so that it's time for today, so I'll go ahead and stop there. We'll continue on with this, talk some more about stats model on Thursday. If people have questions on that, I'll probably go directly into the assignment on Thursday, give a final chance to see if anybody has specific questions about stuff I'm looking for. I know there is one thing, so I do want to show how to create the decision boundary, or at least discuss that. So I'll do that on Thursday as well. So it's one of the things we're supposed to do when you're doing the logistic regression. Okay, yep.
Thank you.